Am I audible?
Yes, sir, fine.
Fine. So, Anpal, wait for 2-3 minutes more. I'm ready, but let some four more participants to join, then we'll continue. ठीक. Okay, so good afternoon, everyone. We continue with our presentations. Actually, today this talk was supposed to be given by Professor Mukesh Kumar Pathak, but he could not be available today. So, am I audible, Anupam, properly?
Yes, sir. Fine.
Slides are visible?
Yes, sir.
Right. So, yesterday we were discussing on the various issues associated with DC to DC converters. Basically, we started that how the power reluctant converters are very much important in various applications, especially microgrid and vehicles. So, if we want to use these converters in these applications, then we should know that how to design the various parameters of these of uh, these converters. So that discussion we were doing, and in that series we had discussed the design of buck converter elements. Then we were discussing the non-ideal, that how in case of non-idealities this performance of the converter uh, alters, and then how to design, or how this energy storage element design of L and C gets changed when there is known idealities in the system. Then we discussed this aspects inductor design. Then we see that inductor requires more. Then we discussed that capacitor design also gets changed. So I just gave these two formula. We have not explained that how this formula comes. Today I'll try to cover because we got some time. So that we will discuss later. Then just I first conclude that where we were. So we have seen that what is the impact of we have taken these values, and after that we have seen that how the non-idealities affect the output voltage. So in order to obtain the same output voltage, we need to increase the duty cycle, and if duty cycle is increased, then output voltage is as per desire. So this was kind of open loop things, that duty cycle we can increase from 0.6 to 0.6415. But this same thing is done in closed loop as well. Closed loop analysis or closed loop control of DC to DC converters does the same thing. There, this output voltage is continuously changed and compared with the reference voltage, and error is generated. That error is processed in the controllers. Then based upon that, duty cycle is manipulated. So there is no need to do it manually, right? So that is the reason that sometimes people use the uh, converter considering as ideal and then do control analysis, because control takes care it. But yeah, obviously when we consider the converter to ideal, then actual practical converter is non-ideal, then efforts put by the controller is more, right? So if we do this analysis by considering non-idealities in advance, then the burden on the control, the efforts put by the control becomes less. That we will see by we will be discussing the controller design, right? So this we have seen. Then we have seen that impact of RC. So as this capacitor, the voltage across the capacitor is is taken as the output. This whatever the voltage across the capacitor is, that is output voltage also. So whatever ripple is there in the capacitor, that will be reflected in the output also. So one of the key point in designing the converters are to keep this output voltage ripple within the specified limit, right? So we have seen that how this ESR impacts the design, how the ESR impacts the output voltage ripple a lot, and we have seen this impact that we keep we have kept on increasing the ESR from, we started from RC equal to 0, that is the ideal case, then 0.1, then ripple increases further, we went to 0.2398, which is RC equal to RC max, right? So RC max is the maximum value of ESR which may be allowed. Then at that ESR value, the output voltage ripple is 1%, exactly 1%. Then if we cross this ESR, then ripple is more. It means the importance of ESR is does play a key role, right? In not only buck converter, in every converter. So we should be very much cautious while choosing a capacitor. Then its ESR must be taken into consideration if we are very much specific about the output voltage ripple, right? So how this RC max value is derived? So I have prepared few slides where we will discuss this in detail, how this value was obtained. So the figure on the right hand side, as I said to you, that like if we take this buck converter, so this output voltage is sum of this capacitor voltage. So this is capacitor voltage, and then this is the voltage across VRC, right? So the output ripple will also be sum of these two ripples, right? Output voltage ripple will also be sum of these two ripples. So that we want to calculate, right? Now, what is this VRC? VRC is nothing but the current flowing in this into RC, and VC is nothing but the voltage across the this capacitor. So based upon that, we will do this analysis. Now, when switch is on, then what is the current dynamics? So that we have seen, this is the IC. IC is nothing but IL minus I naught, or you can say IL minus V naught upon R. So V naught upon R is constant, and basically that is the IL itself. So IL is minus IL itself, right? So this is the 0. It means this waveform is our IC. This waveform is our IC, right? This waveform is our IC. Now IC into RC will give me this VRC, right? And V naught, this V naught C, this voltage is due to the capacitance, and sum of these two will be this output voltage ripple, right? Now our aim is to find the capacitance value such that the output voltage ripple are within the limit, right? Output voltage is within the limit. So when switch is on, then this is the capacitor current equation from 0 to T by 2, right? So this value is 0, this value is T by 2, right? And this, sorry, not T by 2, this is dt, this is 0, and this value is t. So the period between this and this is 1 minus t into t, and half of this means this period is 1 minus dt by 2, right? And period from here to here, total period, this period is dt. So period from here to here is dt by 2, and this period is also dt by 2. So if I measure period from here to here, so this is sum, not here, up to this point, this is sum of dt by 2 plus 1 minus dt by 2, which is t by 2. Right? So this time period we have found. Now next thing is that this value is from here to here, this total is del IL, ripple current. So this value is del IL by 2, and also this value also del IL by 2, right? So these values we are having. Now with the help of these values, we can find the IC equation current for this line, equation for this line we can find, which is the capacitor current. So IC is equal to, so capacitor current dynamics is given by IC is equal to del IL upon dt. So we just follow this equation y equal to mx plus c, right? Where m is from here to here, change in current is del IL. What is the time taken from here to here? That is dt, right? So m, x is t, c is nothing but this value, which is minus del IL by 2. So in this way we find this equation, right? Now we go to the IC equation. So when IC equation is obtained, then we can find VRC, which is nothing but IRC into RC multiplied by ICT. So we'll put it back here. Value of IC will put from here to here. Then we'll get del VRC T equal to RC into del IL T upon dt minus del L. So let's say this is equation 1, this is equation 2. So we put 1 into 2, so we get 3, right? We get this equation 3. Now for the capacitor, if current is given to us, then we can write equation, because we know that IC is equal to C d V upon dt. So VC will be 1 upon C IC dt, right? And if you take it from 0 to t, then VC, this term will also be added, which is the initial voltage at time t equal to 0. So this is the generalized equation for the capacitor voltage, where del Vc 0 is initial voltage. Why we are taking this? If we see again this capacitor equation, then we do not know how much voltage this is. This voltage may be having some value. This voltage may be having some value, right? Now, so del Vc0 is the initial ripple voltage across capacitor T equal to 0. Now we will put the value of IC. Let's say this is equation 4. Now we will substitute value of IC from 1 into 4, right? So this value we are putting del Vc equal to, so this value we are putting in this equation. So del Vct is equal to 1 upon C integration 0 to T. In place of IC, we are putting this entire term here, then dt plus del Vc0. Now we will integrate it and simplify. So after the integration, if we integrate this term, we get del Vct equal to del ILT upon 2C in bracket T upon dt minus 1 plus del Vc0, right? So this term is our del Vct. This term is giving me del Vct during on period, which is like this equation represents this voltage from here to here, here to here. This equation represents this voltage, right? Now this is del Vct, but what is our, I am interested in total output voltage ripple. So what I will do, I will add both of them. So if I say this is on simplifying, I get equation 5, right? This is equation 6. Now in this equation 6, what I will do, put values from equation 3 and 5, equation 3 and 5. So if I put equation 3 and values from 3 and 5, so this is one value which I have put here, plus then this equation 5 is this one, so I'm getting this value. Now this is the total voltage ripple appearing across the output or across the load here at the load terminal, right? During switch on, it means during this period, starting from here to here, right? Now we are finally interested in obtaining the del V naught, right? Del V naught. So what is that? It is the difference. So this voltage will have certain minima, right? But we do not know at what time it is getting minimum value. Similarly, during term of time also, this voltage, output voltage had certain maximum. We do not know at what value of T2 it is maximum. We do not know at what value of T1 it is minimum, right? But if I have this expression with me, then if I differentiate it with respect to T, this will give me the value of T1 at which my this voltage is minimum, right? Similarly, this side, if I differentiate this expression, we will see how this expression is obtained. I'll get the maximum value of del V naught at T2. Now, if I take a difference of these two values, then this will give me output voltage ripple. This will give me output voltage ripple. That is the task we are going to do, right? So now this expression has come here. You can say here also. This expression has come from 0 to T by 2. Now it means this T1 is somewhere between 0 to dt, and that is also less, T1 is less than dt by 2, right? So if I differentiate this equation with respect to t, which I have done here, and simplify for the T1, simplify for the time t, then this time t is t equal to T1, whose value is given this one, and so this is, let's say, 7, this is 8, right? So if I put this value of T1 back into this expression, then I will get this value of del VO T1. So if I put it back here, then in this expression, then I will get value of del VO T1, which is this one, right? Similarly, if I put the value of T1, so this is a total del V node, but it consists of two components, del V RC and del VC. So if I put the same value of T1 in expressions 5 and 3, expression 5 and 3. So this is from 3, this is from expression 5, and this is from expression 7. I can get what is the contribution of del VRC at time t equal to T1. What is the contribution in ripple by capacitor? What is the contribution in total output voltage ripple? Obviously, which should be the sum of these two. And this is this one. So you can see that this, let's say 9, 10, and 11. So this 11 is sum of 9 and 10, right? Now similar analysis we will do when switch is off, because we want to get del V naught T2, right? So when switch is off, that is the period when T is between dt and T. So when switch is off, the capacitor current dynamics is given by, so we will see here, this is our capacitor current dynamics. Just I draw it here again. Right, this one. So this is del IL by 2. This is also del IL by 2. This is GT by 2. This is GT, right? And this period is dt plus 1 minus dt by 2, and this period is t, right? This like this. So now I want to find this current equation. So this current equation is given minus del IL t minus dt upon d dash t, where d dash is 1 minus d plus del IL by 2. So if you put t equal to dt in this, then this term 1 is this. And what is the value of ICT? This is just del IL by 2, so this value, right? Or you can use directly the formula y. You can use this formula again here, y equal to mx plus C. So Y is nothing but ICT, right? What is the M? M is the total change in current, which is minus del IL. How much time is taken? This much time is taken, which is nothing but 1 minus dt. So 1 minus dt, right? And then X is time, and it is also shifted by time dt. So minus dt plus how much is the component on x-axis? So that is del IL by 2. So like that we get this equation of ICT. Now this ICT is for t equal to dt to t, right? Now if I multiply this IC, let's say this is equation number 12 with RC, then it gives me the output voltage ripple due to RC, and due to capacitor itself, del V naught is equal to 1 upon C integration dt to small t ICT dt plus del Vc dt. So this is the initial voltage at time t equal to dt, right? So if you see this Vc, so there is little voltage, some voltage is there, so we do not know what is the value of this. So that voltage is del Vct. So these two expression has come with us. Now we can put the value of IC in these two expressions. So here in this expression, if I put back this value of IC, so from 12 to 14, putting the value from 12 to 14, we get this expression, right? Just we have put value of IC, and we can simplify this. So after simplification, we have got del Vc, right? Therefore, the total output voltage ripple during switch off period is the sum of voltage ripple due to ESR and voltage ripple due to capacitor. So we will add both of them, and when adding, it means we are substituting value from your 13 and 14, 13 and sorry 15. You are putting value from 13 and 15. So if you put this value from 13 and 15, then del V naught, we got this expression, right? Now we can simplify this expression, and we are getting del V naught expression. So this expression, del V naught expression, is nothing but the expression for this particular voltage. So you can see these equations are quite complicated, right? But this complication is due to presence of RC, right? And we want to see the impact of RC, right? How does it impact on the output voltage ripple? We have to do this analysis. We need to do this analysis, right? Now, this del V naught is there, but I am interested in what is the value of maximum value in this entire period. So in order to get the time at which this maximum value occurs, I need to differentiate this with respect to t. So I have differentiated this with respect to t, and when I differentiated it with respect to t, I found value of t2 to be 1 plus dt by 2 minus rc. If I substitute back this value, so let me number the equation. This is 15, this is 16, so this is value of t2 17. So if I put this value of t2 back in these three different expressions, then I will get the contribution by RC, contribution by capacitor, and then this is the sum of these two, that is the contribution total output voltage ripple at time t equal to T2. So that is equation 20. Now I have obtained del V naught T2, and here I have obtained del V naught T1. And you can see here the difference of these two voltages are the my output voltage ripple, right? So the peak to peak value of output voltage ripple is del V naught T2 minus del V naught T1. So we take the difference. So this is the difference. Now here we do not know this del Vc and del Vc at the time t equal to 0 and time t equal to dt. But in steady state, these values are same. So we can put these values to be same in a steady state. So they will cancel out, and then we can simplify this, and finally we get this expression for del V naught, which is equal to del IL in bracket 1 upon 8 FC plus RC square CF upon 2 DD dash. So if we put RC equal to 0 in this expression, then the output voltage ripple, if we put RC equal to 0, then this output voltage ripple is del IL upon 8 FC, right? It is the same as we have obtained in ideal case without considering the effect of capacitor ESR, which you can see here, right? Which you can see here. Okay, but if we consider the RC, then this is the output voltage ripple. So that increases the total output voltage ripple, right? Similarly, we can also find by taking the difference of the voltages at two time instant t equal to t2 and t1, what is the net contribution of RC in this expression? So the net contribution of RC in this expression is by substituting value of this VRC T2 and V del VRC T1. So this is the contribution, total contribution in peak to peak ripple voltage, and the contribution by capacitor is this one, so that we can analyze. Now we are plotting these equations. So let's say 1920, then it is 21, 22, 23. So if you plot 21, 22 and 23 with respect to RC, then what you are observing here, that this green one VRC, that is continuously increasing with the increase in RC, right? So this is continuously increasing with the increase in RC. That is the first observation. Second observation is that if you are increasing the RC, then what is happening? The ripple due to capacitance, that is continuously decreasing. And if you see the total V naught, that is also increasing with when we are increasing del VC. But what happens at certain value of RC comes here, at which the output voltage ripple is lesser, and the ripple which is due to RC, that exceeds, and that is not possible. Why it is not possible? Because this total ripple should be more than the ripple caused by RC itself. So it means this value is not feasible after RC equal to RC max. So that's what I have written here. From this figure, it is observed that with an increase in ESR, del VRC increases at a faster rate than del VC decreases, thereby net increase in del V naught. However, as value of RC increases beyond RC max, the voltage ripple del VRC becomes higher than del V naught, which is practically impossible. It implies that the capacitor is no longer able to keep output voltage ripple within the specified limit for RC greater than RC max. This figure shows that as long as capacitor ESR value is less than RC max, the output voltage ripple is less than 0.12 volt. Right? You can see here these output voltage ripples are given. As desired within 1% of output voltage. The analytical relationship for this RC max we will derive now. Right? So what is this value of RC max? So for that purpose, let us say the maximum output voltage which we want is del VOM. This is the desired output voltage. Therefore, this capacitor should be designed in such a way that the actual output voltage ripple OVR, that should be less than this, because this is the maximum what we want and this is the actual, right? So that should be always less than the reference value, right? Now this del V naught value we have derived just here. Del V naught value we have just derived here. It means this value should be less than VOM. So this value I have just put that value here, that should be less than del VOM. right? Now I need to simplify this because I want to know the value of C minimum. I want to know the value of C minimum. So I need to solve this inequality and I get this expression, right? So this is a quadratic constant in C. Its solution is obtained to get the minimum value of capacitor C. So this quadratic equation is solved for C and we get this expression. Now this C minimum is dependent upon RC, or it is a function of RC, right? So this expression gives the required minimum value of capacitance C with RC less than RC max, right? Now, how to find the RC max value? So this capacitance value to be realized, what should be the condition? That this value should be realizable. So this is okay, this is real value, but this value which is within this square bracket, that value should be positive, right? If this value is not positive, then this square root of negative value becomes imaginary and capacitance value we cannot find, right? So C minimum to be a real quantity, the following condition must satisfy. So this condition must satisfy, this term should be greater than 0. Now if we simplify this, then we get the value of RC should be less than equal to 2 square root d dash del VOM upon del VIL. Well, right, therefore the maximum permissible value of RC for the desired, इसका मतलब what is the meaning of here, that RC should be less than this. It means what can be the maximum value, which is equal, right? So if I take this equal from here, then that becomes the maximum value, right? So this maximum value is depending upon D duty cycle and output voltage ripple desired, and also on the ripple current, right? So we have this del VOM is given to us, right? So substituting into this gives the worst value of now if I put this value of C max back in this will give us the worst case value of C minimum. So obviously if I put this value here, then this part will go away, this becomes 0, and from here C minimum at RC equal to RC max comes out to be 1 upon 4F del IL del VOM, this one. And what was the value for RC equal to 0? This was the value of RC equal to 0. It means the required value of capacitance becomes double. It becomes double at worst case RC. It becomes double at worst case RC, right? So, see the impact. If we we neglect this inclusion of RC, and we just choose the value of capacitance to be very tight using the ideal formula, then the performance of the converter may be deteriorate, right? May be deteriorate, and how it will be deteriorate, that will be decided by these expressions, right? So this was our value of RC max, right? We can put now value of del IL. So we already know del IL when we write equation for switch on and switch off. So that value of del IL we are putting here. So 2 square root d dash del VOM divided by this value of del IL. We can simplify this and we get this final expression. So what this expression says that, value of RC max is depending upon F. It is directly proportional to frequency. So if you are using the frequency to be very high, right, then we have RC max to be more. It means I have flexibility that I can use a capacitor which is having more ESR, because due to increase in frequency, my reference for RC that has increased, Right. So what I'm saying, just let's say we were using 20 kilohertz frequency, for example, let's say, and value of RC max for that was somewhere, let's say, 0.2 ohm. Right. Now you have used, and I have a capacitor which is value having RC equal to 0.3 ohm. Right. Now, if I am using this capacitor at 20 kilohertz frequency, then this RC is greater than RC max. It means it should not be allowed, otherwise it will deteriorate my performance. But if I use the same capacitor at 40 kilohertz, so now as per this calculation at 40 kilohertz, my RC max value, and meanwhile, please note that other values we are not changing, other values of components we are keeping to be same. So in this case, RC max now, because frequency is doubled, so it is proportional to F, it becomes 0.4 ohm. So if I use the same capacitor with RC equal to 0.3 ohm, in this case, that is allowable. So that is a conclusion, right? If you increase the frequency, then we have flexibility in selection of capacitance in terms of ESR, right? So the relation depicts that for a specified output voltage ripple, the maximum permissible value of ESR is proportional to switching frequency. Therefore, as the switching frequency of converter increases, the power supply designer is allowed to use the high ESR capacitor without violating the output voltage ripple constant. This figure here, this figure shows the variation in RC max with reference to frequency. So this figure shows the variation in RC max is this side with frequency. So it's obviously proportional. So if you double the frequency, then ESR also gets double. That's the whole idea. Like if it's like 20 kilohertz frequency, if it's a zero point 0.3, then at 50 kilohertz frequency, it's a zero point 0.6. So it just get double, right? It is observed that if switching frequency is 50 kilohertz, the designer may use a capacitor with an ESR of 0.6 ohm, whereas at with a 20 kilohertz frequency, this value is limited to 0.24 here, 0.24, this one. It is also worth noting that as frequency increases, the required value of capacitance decreases. Obviously, so as frequency increases, that we have already discussed, the value of capacitance gets decreased. So we can see here that how important this analysis is and how to select a proper capacitor. You can read multiple papers are there where they discuss the impact of this ESR on output voltage. Right. So this was some of the discussion which was left yesterday. I have completed it. Now, okay. So after the buck converter, next comes DC to DC boost converter. So we will do analysis of this very quickly. So first we take this to be ideal, right? And all the assumptions remain same, which we have done for buck converter. So almost for all the DC to DC converters, these assumptions remain same. That converter is operated is considered to be in CCM, converter is in steady state, right? And capacitor output capacitor is very large, so that its value can be assumed to be constant, like that. Its voltage across this can be assumed to be constant. So this is a circuit. It also has one capacitor, one inductor. So let's denote that voltage and current direction. So this is the current direction, this is the voltage, this is capacitor current, this is capacitor polarity, this is the R output polarity, right? This is the output current. When switch is on, duration is 0 to dt. When switch is off, duration is t till t. Okay. So when switch is on, then this energy is being stored in this inductor, and this is the capacitor and here was our diode. So because switch is on, so this plus comes here, this minus comes here, and diode becomes reverse biased. So diode becomes reverse biased. Now in this case only capacitor feeds to the load. So we can see that this is the direction of current. So here if you are seeing this means this current will flow like this. This current will flow like this. So IC is negative in this case. It means capacitor is being discharged. Right? So when at t equal to dt, this switch is off. It is turned off. Switch is turned off. Right? It's just like we use IGBT or MOSFET. They are self-commutating devices. So as long as we give them the pulse, they are on. As soon as we withdraw the pulse, they becomes off. So we withdraw the pulse. Now because this inductor current was in this direction and current was increasing like this. So now suddenly this path was interrupted. This path was interrupted. Now current cannot, because this path is interrupted now, current cannot fall through this. Now it look for another path. In this attempt, it gets decreases. Due to this decrease, now this voltage polarity gets changed, right? So earlier this was plus minus like that, it becomes minus plus. Now this voltage along with the source voltage becomes greater than this output voltage, and the diode sitting over here that gets forward bias. I repeat again, the path, this current path, we made this switch to be off, then this path is interrupted. Due to this interruption, current start to decrease, and when current start to decrease, then LDI by dt, time change in time is positive, but change in current is negative. So overall this voltage is negative. So this polarity becomes like this, minus plus. So Vs plus this voltage, because this polarity is also like this voltage becomes greater than V naught, due to which this diode becomes forward bias and the inductor flows through this path. Inductor flows through this path. Now the voltage across this inductor is Vs minus V naught only, which is negative in case of boost converter because Vs is less than V naught, due to which negative voltage is there. It means current keep on continue to decrease, right? And now this current continue to decrease, and now the source feeds the load as well as charges the capacitor. So capacitor is being charged in this case, which was being discharged in case 1, right? So that's how this boost converter works. Okay, well, so this is just the assumptions which we take, steady state conditions, adjust and all those assumptions. I'm not going to repeat this. Now let us see how the equations does follow. Equations do follow. So in boost converter, when switch is on, then this output voltage VL is equal to L di by dt, right? So we can write from here di by dt equal to Vs upon L, where Vs is the supply voltage, right? So from here we can write del IL by dt, del IL by dt equal to Vs upon L. So from here del IL comes out to be Vs upon L into del T. So value of del T is dt. So this is the value of del IL. You can see here when switch is on, switch is closed, then this is the output voltage. Sorry, not output voltage, this is the VL, inductor voltage. When switch is off or switch is open, then this is the voltage which is Vs minus V naught, right? And when positive voltage Vs is there, then inductor current increases, inductor current decreases. This is the diode current, because during on period diode is not operating, so current through diode is 0. and current through diode is same as inductor current when switch is off, right? Similarly, if I talk about capacitor current, then capacitor current is okay. So from here, del IL comes out to be Vs upon L into dt, right? And during this period, IC is nothing but minus I node, which is minus V node upon R. If I apply KCL here, there is no current from here. ID 0, IC is here. So this ID is equal to IC plus I node. ID 0, IC plus I node. From here it comes. Okay, so this is I node. Well, now, so this is IC equal to minus V node upon R during this period, right? Similarly, if I take the case 2 when switch is off, then VL is Vs minus V naught, right? So this is V naught, Vs minus V naught, which is equal to L di by dt. So from here, dIL by dt is equal to Vs minus V naught upon L. Now you can see here this Vs is more than Vs is less than V naught in boost converter. So this slope is negative. This slope is negative, it means current decreases in this mode. So inductor current is decreasing when switch is off, right? Now from here, del IL comes out to be Vs minus V naught upon L into del T in this period is this. This is 1 minus D into T. So this is 1 minus D into T, right? So now we have del IL with us. This del IL is when switch is open. Switch is open, and that del IL is with us when switch is closed. Okay, so now we have these two equations with us, and we know that the net change in the inductor current over one period should be 0. So we just, the net change in the inductor current over one period should be 0. So what we do, we just add these two things and it should be 0. So I'll put back these two values, IL open and IL closed here, IL closed and IL open, that's to be 0. And after simplification, we get this equation. V naught equal to Vs upon 1 minus Vs upon 1 minus D, right? So obviously, if I put D equal to 0, then V output is equal to Vs. If I say D equal to 0.2, then V output equal to Vs upon 0.8, which is 1.25 Vs. If I say D equal to 0.5, then output voltage is Vs upon 0.5, that is 2 times Vs. If I say it to be 0.8, then this is Vs upon 0.2, 5 times, right? And if you say duty cycle equal to 0.99, then V output will be Vs upon 0.01, that is 100 times Vs. If I say duty cycle equal to 0.999, then output voltage becomes Vs upon 0.001, that is 1000 times Vs. So it seems that if I put any duty cycle, then I can get the output voltage to be whatever times I need, right? But this is not true. Shortly we will see it, right? So if I just upload this expression, duty cycle versus output voltage, then at D equal to 0, my output voltage is same as Vs, right? And as duty cycle keeps on increasing, then this keep on increasing, and the output voltage at duty cycle 1 becomes infinite theoretically, right? So the same expression may be and what is the practical way that we will also discuss. That is the wonderful results. We will be surprised that boost converter is does not work in this way in practical case, right? The another way is volt second equations we can keep. So volt second equation means we have inductor voltage when switch is on. So when switch is on, then inductor voltage we take. So what is this inductor voltage when switch is on? This is nothing Vs, and here it is Vs minus V node. So yeah, so Vs into dt plus Vs minus V node into 1 minus dt, that should be equal to 0. Volt second equation balance. So from here t cancel out. So d into Vs plus Vs minus d into Vs minus V node 1 minus d equal to 0. This will cancel out. Output voltage will be Vs upon 1 minus d. Okay, so this is the output voltage. So this way also we can find derive the output voltage. Now next is design of inductor. How to design inductor for this case? So there are various ways. Let us see one way how to find the average inductor current. So this is the output power. What is the output power? P node equal to V node into I node, right? So V node square upon R, that is the output power V node into I node. And what is the input power? V input or Vs into Is. And inductor is connected here. So if this is the Is, so same is the IL, right? It means whatever the average value of Is, same will be the average value of IL. So Is is equal to average value of the source current is equal to average value of this inductor. So Vs equal to IL, that we have written here. Now this Vs IL, that should be equal to V node into I node, right? That should be V node into I node. And okay, we can write like that Vs IL equal to V node I node, we can write as V node square R, right? So from here IL comes out to be V node square upon R into Vs, right? Now we have the value of, so depending upon in which terms we want to find the value of this, we can put the value of V node here. So V node is nothing but, we can element either V node or Vs from here. So if we want to element the V node, so V node is Vs upon 1 minus d square divided by R Vs. So this is Vs upon R 1 minus d square if we take in terms of Vs. If we take it in terms of V node, then what we can do, we take V node square upon R to be as it is, or you can say like that, V node upon R into V node upon Vs. And since uh, V node equal to Vs upon 1 minus d, so Vs upon V node, Vs upon V node is 1 minus d. So it becomes V node R into 1 minus d. That means IL is equal to I node into 1 minus d. Okay, so from here we can get the value of IL. And obviously this could be obtained directly from here itself. It could also be obtained directly from here itself. So we got the average value of inductor current now. Now next is to get the minimum and maximum value. So this is the inductor current. So this is maximum value IL max. This is minimum value. The difference between these two is ripple current del IL. So IL minimum is nothing but IL average plus del minus for IL minimum it's a minus del IL by 2 and IL max is equal to IL plus del IL by 2, right? So these two equations are there. Now we already know the value of del IL, so we will just put the value of IL and value of del IL, right? Now next is that how to get the inductor design. So for inductor design, what we do, we put this I minimum to be 0, right? I minimum to be 0. So by substituting this R minimum to be 0, I minimum to be 0, then we get Vs 1 minus d square R minus Vs dt upon 2L to be 0. Vs will cancel out. So from here, I'll get 1 upon 1 minus d square R equal to d upon 2LF. Okay, so what we get from here, L is RD upon 1 minus D square upon 2F. So this is the value of inductance. Which inductance? Critical inductance, which is just letting us IL minimum to be 0, right? IL minimum to be 0. So if IL minimum is not kept to be 0, or it should be having some positive value for CCM, then what we should do, we should choose L, which is 5 times L critical, or 5 times to 10 times L critical. So this is how we design the value of L. Yes, here, right? So you can see this formula. So the product of LF minimum should be given by this. If you fix the switching frequency, then L minimum is given by this formula. Okay, so instead you simplify this, you directly, because you have this particular equation, if you directly want to know the value of inductance in terms of del IL, then we can use these formulas as well. Okay, so this is how we find L critical. Not L critical, sorry. This will be actual L only, because you are given del IL. You are given del IL directly, right? Well, so how to do the capacitor design in case of boost converter? So capacitor design, for capacitor design, we know that we need the waveform for capacitor. We need the waveform for capacitor current. So this is 0, this is GT, this is T. This is on period of switch. This is off period of switch. So during on periods of switch, capacitor is discharged only, capacitor is discharged, and during on period of this, capacitor is charged. So if I put, let's say, just if I draw the waveform of output voltage. So capacitor is being discharged using constant current. It means capacity charging is discharging linearly, right? It is discharging linearly. And during DT to T, capacitor is charging. So capacity charging, but this current is itself linear. It means its integration will be non-linear. So the output voltage will be non-linear. It means this charge is in this pattern. So like this, it will be there. Charging, discharging, then charging, right? Like that. So this is VC max, V output max, and this is V output minimum. The difference between these two is del V naught, output voltage ripple. So that's what we want to find. Now, as we have seen earlier, the del Q is the net stored charge, or you can say discharge charge. So that is equal to C del V naught. Now this del Q is nothing but the right, like that. So del Q is nothing but integration of I dt, right? So if I want this from this period 0 to dt, so it will give me this area under this curve will give me the charge which is, you know, dissipated. Charge which is dissipated means charge which is discharged basically, which is fed to the load. So that will be there. So I can write this equation over here, or I can directly find the area. So this area is nothing but minus I, not minus, I'll not use minus, I node into, because this current is I node and base into height. So I node dt is that del q, right? And what about the so this equation and this equation I'll compare. So C del V node equal to I node dt, where I node is V node upon R into dt C del V node. So from here, del V node upon V node comes out to be d R C, and T I am writing 1 upon F. So this becomes del V node upon V node becomes d upon RCF. So this is the output voltage ripple. If output voltage ripple is given to us, then we can find the value of C minimum, which is D upon RF del V node upon V node, right? So this is the formula which gives the C capacitance, minimum value of capacitance, right? So now if there is a equivalent series resistance also available here, then what we can do, we can have the output voltage in that case del ICRC equal to IL max into RC, right? Because if that is there, then due to ESR, this voltage will be there, right? This ripple voltage due to ESR will be this one. This is the IL max, right? So if it is getting multiplied with the R, then this becomes R into IL max. Well, so any doubt so far, please ask. If you have any doubt in today's class so far, for last 1 hour 15 minutes. Any doubt? No. Okay, well. So let us see the non-ideal converter, boost converter. How does it behave? So we are considering just one non-idealities, and we will derive its equation. So when switch is on, that is from 0 to dt, we will derive its expression. Then what is the equation? Like this. We have considered one non-ideality only, that is the RL, inductance resistance only, ESR of the inductance only. And when switch is on, then this is the case. Now switch is off, sorry, diode is off. So this is our equations, right? We are interested in finding the output voltage expressions, right? So this is plus minus IL plus minus V input, right? V input or VG, you can say VG, IL, inductor RL, IL, like that. So in this case, what is the inductor voltage VL? That is nothing but VG minus IL, RL, right? And because we want to find only output voltage, I am writing just only inductor equations. So when switch is off, then that is the period to T. This is RL, this is L. So switch is off, it means this switch is off, and now diode is on. So diode is on, switch is off, and this is capacitance, and this is resistance, and this is our output voltage. So in this case, this inductor voltage VL is equal to VG minus IL RL minus V node, right? Now equation 1, equation 2. Also, you can write here IC equal to, this current IC equal to minus I node, which is minus V node upon R. So let us give this to equation number 2. Let us this to equation number 3. And in this case, this IC, this is IL. So this IC is equal to IL minus V node upon R, equation number 4. So this equation we have obtained. Now for steady state analysis, the first principle is bold, second balance. So bold second balance, when we are doing Vg minus IL RL into dt plus Vg minus IL RL minus V node into 1 minus dt equal to 0, right? So this t will cancel out. Vg minus IL RL, that is common to both. So this will be Vg minus IL RL d plus 1 minus d, and another term will be minus V node 1 minus d equal to 0. So this is 1. It means V node is equal to Vg minus IL RL upon 1 minus d L. So this is output voltage. But here output voltage is in terms of IL. So we need to find the IL. So that is possible when we do capacitor charge balance. Right? So capacitor charge balance will be when I minus I naught into, or you can say V naught upon R into dt plus IL minus I naught, this equation IL minus I naught into 1 minus dt will be equal to 0. So because I naught is both sides, so I can take t will cancel out anyway. T will cancel out. So minus I naught I can take common. So it gives t plus 1 minus d plus IL 1 minus d equal to 0. So this terms becomes 1, and I naught is equal to IL 1 minus d. Right? So from here, the value of IL comes out to be V naught upon R into 1 minus d. Right? Now, if I put back, how many equations it becomes? 1, 2, 3, 4. Let's say this is 5, and this is equation 6. If I put equation 5, not 5 into 6, 6 into 5. If I put 6 into 5, then I will get V node equal to Vg upon 1 minus d minus ILRL. So RL is there, IL is this one, right? We can take V naught to be this side. This is 1 plus RL upon R 1 minus d into Vg upon 1 minus d. So from here V naught comes out to be Vg upon 1 minus d into 1 plus RL upon R 1 minus d. So you see, if we keep RL to be 0, then this expression is same. If we keep RL to be 0, then this expression is same as it was in ideal case, right? But when non-idealities is there, then this expression is valid. So let us say this expression is saving, right? So if I again simplify this expression saving, then let's say this is V node equal to Vg. I take 1 minus d to be some mistake is there. Uh, yes, here, yes. This is Vg upon 1 minus d minus RL. This will be square. Yeah, RL 1 minus d was already there. So you can say just this RL upon 1 minus d was there. I put just this. So this will be square and this will be square, right? So if I simplify this, then this is Vg into 1 minus d 1 minus d square plus RL upon R. Okay. So if you put here d equal to 0, then what is the output? Vg upon 1 plus RL by R. If you put d equal to 1 here, then what is the output? If you put d equal to here, then Vg into 0 upon RL by R. So that is V output is equal to 0. What happened here? Previously, in this case, we were expecting here in this case that if duty cycle reaches to 1, then output voltage should reach to infinite in ideal case. But here what we are seeing that if duty cycle is 1, then output voltage becomes 0 in non-ideal case. It means what is happening? This non-idealities, right, is in presence of non-idealities, the output voltage is not infinite. It is not infinite, it is restricted. So this same thing I have plotted here. You can see this, right? So this is the expression what we have just arrived, this expression. If we put d equal to 1, then it is 0. So duty cycle started from here, d equal to 0. Duty cycle keep on increasing, keep on increasing, keep on increasing. Then if RL is 0, then this should go to infinite. If RL is having some value, then this is going increasing, increasing, reaching to maximum. Then this is decreasing and going to 0. And further, because here this RL by R ratio, it was 1%. So peak was at this point, right? Now this RL by R ratio has been increased, means non-ideality has increased. So what is the impact? Now this value of D at which maximum voltage is occurring is further decreasing, right? So here it means non-ideality is lesser. So value of D at which maximum voltage occur is more and maximum voltage is more. But due to increase in non-idealities, the peak also get reduced and the value of duty cycle at which peak is there, that also get reduced. And as this RLY keeps on increasing, then what happens? The output voltage gain keeps on reducing. And you can see this is the reason that output voltage cannot be whatever we want from a boost converter, right? Because a practical boost converter has non-idealities present in this. So with any duty cycle, sometimes we do experiments, then we try to change duty cycle, and we always expect okay, output we keep on increasing duty cycle, then in boost converter then it should increase, it increases, then we keep on increasing duty cycle, then suddenly it start decreasing. We see what happens. eh? As theory says, duty cycle increases, then output voltage should increase, but it is not increasing, rather it is decreasing. This is the reason. And if you see here, this particularly this, no, so this, if I take all these peak points, then this is the locus, right? So all the values to the left of these peaks, they are realizable, they are stable values, because duty cycle, when we increase duty cycle, then it is expected output voltage should increase. It means this region is stable region, but this region this region is unstable. So this region is unstable and this region is stable. Why so? Because if you see on the right hand side, on increasing duty cycle, the output voltage is decreasing, which is not the case, right? It means if you keep on increasing duty cycle beyond that, then your converter becomes unstable. Your converter may become unstable. So you have to keep duty cycle to the left of maximum value. It means you should know the maximum value, right? And this maximum value is restricted by the value of ESR, right? So we can find that what is the maximum value of this. So, or maximum value of duty cycle. So what we need to do, this expression is with us, right? This expression is with us, and we can use this expression, right? So I'm just writing, let's say this is the voltage gain V naught upon V input, which is nothing but 1 minus D upon 1 minus D square plus RL by R. So what I need to do, I need to differentiate this with respect to D. So let us differentiate this. So 1 minus D square plus RL upon R whole square, 1 minus D, no, 1 minus D square plus RL by R. 1 minus D differentiation is minus 1, then minus 1 minus D into differentiation of bottom terms. So 2, 1 minus D, then minus 1 plus 0. That should be equal to 0. So the denominator goes into 0. So what is left with? Left with is RL upon R plus 1 minus D square with minus sign. Okay, this goes that side. Then what is left inside? This is 0. So minus minus, this is equal to, this is equal to 2, 1 minus D square. So if you again do it, then it is 1 minus D square equal to RL by R. So from here 1 minus D comes out to be, because this value should be positive, RL by square root. So from here D comes out to be 1 minus square root RL by R. So this is the value of duty cycle. This is the value of duty cycle at which maximum value of M will occur. So you can see from here, right, as RL increases, then value of D at which maximum voltage occurs, that keeps on decreasing, and that's what we have seen here also. And what is this value of maximum gain? So let us find this. So we put this value of D max, or 1 minus D equal to square root RL upon R back in this expression. So what does this give us? M equal to 1 minus D equal to square root RL upon R divided by RL upon R plus RL upon R, right? So this is 2 sorry. So this is square root RL upon R. In denominator it is 2 RL upon R. Right? So uh, yes. So it becomes 1 by 2 square root R upon RL. There is some mistake actually. That is okay. Yeah. So this is the value of voltage gain. So from here, what we observe that as RL value is, let's say 0, then M should be infinite. Gain should be infinite. But if as RL keeps on increasing, then what is happening? M keeps on decreasing. M keeps on decreasing. It means voltage gain keeps on decreasing. So we can see the impact of increasing this RL, right? So it is, you can see here the importance of the value of ESR on the performance of converters. Okay, so we take one example here just to understand the things. We need to design a boost converter for which output voltage is 30 volt and input voltage is 12 volt. So design for CCM operation and an output voltage ripple of less than 1%. So del V node upon V node, we are given 1%, which is 0.01. The load is a resistive load, so value of R is given to us 50 ohm. Assume ideal components for this. So these 4 parameters are given to us, design parameters, and we need to find the value of L and C, right? So because input is given, output is given to us, so with the help of, we can find the duty cycle. So duty cycle D is calculated as 0.6, right? Now next is to calculate the L. So L minimum formula is D into 1 minus D square R upon 2F. R is known to us, D is known to us, F is not known. So F, as I said earlier, that is the things which need to be decided by the designer. So let us choose the a realizable frequency, that is 20 kilohertz. So we put 20 kilohertz also here. So we get the value of 96 microhenry. So this 96 microhenry is just corresponding to the boundary case. But we need to have CCM operation, right? So what we can do, we can choose any value which is greater than this. So we can take 120 microhenry, even we can take 500 microhenry, right? So more the inductance, then obviously less is the ripple, but the size and cost will increase. So we can choose the optimum value of this inductance, right? Now see capacitance value. So capacitance value formula is D upon RF into output voltage ripple. So we put all these values, and the value the numeric value comes out to be 48 microfarad. Numeric value comes out to be 48 microfarad. So now because 48 microfarad may not be available directly in the market, so what we can do, we choose a capacitance value to be 100 microfarad, right? Which is easily available, 100 microfarad. But yeah, this value of capacitance which is chosen, that should be more than the uh, C minimum, right? So any doubts so far? Any doubts so far? No question. Okay, well. So next is the design of. So we will take 5 minutes break over here. Anupam, Anupam. We will take 5 minutes break over here. Okay.
Okay.
हाँ. Okay, well, so let us go ahead. Yeah. So now the third converter is DC to DC buck boost converter. So the same analysis will follow. We will quickly finish this. Then this is the circuit for buck boost converter. So as we can see that in buck converter, the output voltage was less than the input voltage, and in boost converter, the output voltage was greater than the input voltage. Just buck converter. Yes. So in buck converter, like output voltage was less than input voltage. In boost converter, whether it's ideal or non-ideal, output voltage was greater than V input. But in buck boost converter, both possibilities are there, right? So this is the circuit. Now when switch is on. So this switch is on now. Now this is the inductor. It is carrying the current in this direction. Let's say this is IL. So IL is being carried in this direction. And now switch. This diode is off. This diode is off. Why this is off? Because the switch is on. Now this entire voltage plus minus, and this is uh, plus minus. So this diode is reverse bias in this case. Now we can write the equation VL, which is the inductor voltage VL, is equal to Vs, which is equal to L di by dt. So from here dIL by dt equals Vs upon L. So this is the first equation which we obtained, and with the help of this equation, because Vs is the input voltage which is always positive, so this is always greater than 0. Now del IL upon del T. So from here del IL is equal to Vs upon L into dt, that we uh, get, right? So inductor voltage equations, if I put Vs is equal to VL, this one, and the due to positive slope, inductor current is increasing, right? Now we can solve it for del IL. So this is the equation. Now when switch is off, that is dt to t, switch is off. Now because inductor current does not have any path, so this diode will be turned on. Now this inductor current will carry this current. This inductor current will have a path through this diode, and this diode will be on now, right? So in this case, the equation. And one more thing, as I said earlier, this polarity is opposite of the input voltage. So VL is equal to V naught equal to L di by dt, right? This is VL, and we have taken this to be positive sign like that. So VL equal to V naught equal to L di by dt. So di by dt is equal to V naught upon L, right? And as I say, in buck boost converter, this V naught is negative. So this value is negative, less than 0. The slope is negative. It means current will decrease during switch off or switch open. So current is decreased. The value of this del IL we can find using del IL upon del T. So del IL del T is 1 minus dt this period equal to V naught upon L. So from here we can find del IL closed to be V naught upon L into 1 minus dt. So I think that it's already written here. So we have found del IL closed and del IL open. As per the steady state conditions, the net change in the inductor current should be 0. So del IL closed plus del IL open, that should be equal to 0. We have put both the values like that. This here we simplified. Now this is the expression which we are obtaining, V naught equal to minus Vs upon B upon 1 minus D. From here we can get the value of duty cycle also. So what we see here, that output voltage is negative. right? And it has the opposite polarity of Vs, right? And this expression, so if I take the magnitude only, so this is Vs into d upon 1 minus d, right? And if I put the duty cycle to be, let's say, 0, then what is the output voltage? 0. If I put duty cycle to be 0.25, output voltage is 0.25 upon 0.75, that is 1 by 3 into Vs. If I put D equal to 0.4, then output voltage is 0.4 upon zero point 0.6, right? That is 2 by 3 of Vs. If I put D equal to 0.5, then output voltage is zero point 0.5 upon zero point 0.5, that is equal to Vs, right? But if I put D equal to 0.6, then output voltage is zero point 0.6 upon zero point 0.4, that is 1.5 Vs. If D is equal to 0.8, then output voltage is 0.8 upon zero point 0.2, that is 4 times Vs. So what we are seeing here, that if duty cycle is greater than 0.5, then all these output voltage are greater than Vs. It means boost operation. Here this is buck operation. So if I plot this duty cycle and output voltage, so D equal to 0, this will be 0, and D equal to 0.5, this will go up to Vs, like this, like this, like this, it will go. Okay, at D equal to 1, this should go infinite. If you put D equal to 1 in this, it should go ideally infinite, but it does not happen. In practical case also, it has to come down. So this is how this boost converter analysis is there. So similar to other converter, we can use the volt second valence again, which also gives the same value. We are not going to repeat it. Now average inductor current. So the same way we can do. This is our converter circuit. Now V output, I output should be equal to V input, I input, right? So now this, if you see, this is the inductor current, right? Like this is the inductor current, right? But if I plot only the diode current, because average capacitor current is 0, so load current will be same as diode current only. So if I plot the diode waveform, so diode waveform are available with me when only I am having switch to be off. It means during this period only. This is the diode current, right? This is the diode current. It means I output will be equal to I output will be equal to 1 minus d times IL. But if I talk about input current, then input current will be available when switch is on. So input current will be this one. It means my input current will be d times IL, right? D times IL. So if I put these values here, now I am interested to find the let's say inductor current. So V node into I node equal to Vs into Is. So Is or I in, so that is D into IL, right? So IL will be equal to V node upon Vs into I node upon G, right? So V node upon Vs is D upon 1 minus D. So this is I node upon D. So IL is equal to I node upon 1 minus D. So, and this is directly from here also we can get. So this way we can find the average inductor current, right, which is required for us. So average inductor current is nothing but V naught upon R into 1 minus D. Now minimum and maximum currents we can find again same. IL max is equal to IL plus del IL by 2, similar to other converters, IL minimum equal to IL minus del IL by 2. Del IL values we already know, IL values we already know. So with the help of this, we can find minimum and maximum current. Now we can also find the value of L minimum. So for L minimum, we need to keep IL minimum to be 0. So this term should be 0. It means Vs upon d r 1 minus d square, that should be equal to Vs d upon 2 LF. D will cancel out. So from here L critical, that comes out to be R 1 minus d square upon 2F, right? This one, R 1 minus d square 2F. So this is the minimum value of or critical value of inductance, and the actual value of inductance can be greater than this for ensuring the CCM operation. Now next is the capacitor design. So when switch was on, then this diode was off. So entire current was fed by the capacitor. So capacitor was discharged like this, right? And when switch is off, diode is on, then the value of capacitor current, this is IL minus V naught upon R, right? So this is kind of similar waveform which we had in boost converter, right? Which we had in boost converter. So same way we will design the capacitor as we had done in boost converter, right? So same formula, del Q equal to C del V naught, right? Now del Q is the area under the curve, ICDT, right? So this area under the curve is nothing but V naught upon R into dt. Now this should be equal to C V naught upon R into dt. So from here C comes out to be del V naught upon V naught. C comes out to be d upon R F del V naught upon V naught. So this is the value of C. If C is given, we can find the per unit ripple. Del V naught upon V naught equal to d upon R C F, right? So if similar to that, if there is ESR present in this, then we can get the we can add this value also. So this value is and this value to this value, that is the IL max. So we can add this IL max into RC into whatever del V naught is coming from here, that will give us the total ESR. Okay, so with this we complete this analysis of DC to DC converters, and same analysis can be followed for other types of converters as well. And we have seen that what is the impact of this ESR on the performance of converters, right? So now next topic is mathematical modeling of DC to DC converters. So if any questions so far, please let me know. Then we will go for this new topic, mathematical modeling of DC to DC converter. If there is any question, please ask. In 5 minutes, we will start this new topic, mathematical modeling of DC to DC converters. If you have any query meanwhile, please ask. Okay, so now we'll start this new topic in a couple of minutes. Please ask if you have any question. Okay, well, so we start this new topic, mathematical modeling of DC to DC converter. So there are various techniques for mathematical modeling of DC to DC converter. So first we will try to understand that why this modeling is required for any physical system, not only for converters itself, right? So when we say we are doing mathematical modeling, then it means there is something physically available. We are just capturing its dynamics and we are making its equivalent model. So why it is required? Let's say some plant is there. This plant is existing. Maybe it's a converter or maybe any other physical plant is there. Now this physical plant is running. It's, let's say, 20 years old, and now I want to improve with the aging. Some performance of this plant has been deteriorates, right? Now I want to improve the performance of this plant. So one way is that we can replace the plant itself, then replace it with new plant. So that is not the feasible case. But if we can add something in this plant, and with addition of that some device, if performance of the existing plant improves, then it's all fine, it's all good, right? But plant is already running, so no one will allow us to do experiments on that running plant, right? So what we can do in that case, how we can invent the new device which can fit with the existing plant and give us the required performance, improved performance, right? So what I can do, I will capture the dynamics of that particular plant. So this plant is made up of various components, right? So I will try to mathematically model the behavior of each components, then combine them and obtain the complete model of the plant. Now, depending upon how accurately I have modeled this plant, means it's a kind of replica. This mathematical model is the replica of that physical plant, right? So more accurate I model this plant, more accurate this is the replica of that plant, right? Now, once this model is with me, having all the dynamics of the system, then I have various tools with me, right? We have simulations, we have various control tools, right? So on based upon that mathematical model, I can develop some controllers, I can develop some devices which will improve the performance of this existing plant, right? So I can try n number of times, n number of iterations I can do, that which one gives me best performance, that I can say okay, it may fit for my physical plant, right? So once I am satisfied in my simulation, mathematical simulation which I am running on the plant, plant's model, not on actual plant, and once I'm satisfied with my controller, then what I will do, I can make a, you know, prototype of that plant, hardware, physical prototype, and use my device or controller, whatever I design on that plant. If it is on this prototype, right? If it is working fine, then I can say, okay, now my device may work on existing plant also, and I can try on that, right? So it means my mathematical model is helping me to get the dynamics of original plant and allowing me to develop a number of devices, a number of controllers which will be suited for him, and then select best one out of those a number of devices. So that is the reason we go for mathematical modeling. Now it depends upon how accurately we can model the plant. The more accurate we model a plant, then the more accurate we can design a controller for this, right? So in this in this topic, uh, particularly we will talk for DC to DC converters. Then we have various mathematical modeling techniques. So like converters has elements, inductor is there, capacitor is there, switch is there, diode is there, right? So for these different elements, we have certain dynamics, right? Inductor current is there, inductor voltage is there, capacitor current, capacitor voltage, in switch current, switch voltage, diode current, diode voltage. So these parameters are there, right? So how the these voltage current have a relationship with inductance, capacitance, like that. So that dynamics we will try to capture in our mathematical model and then simplify it, right? So there are multiple techniques that exist. So we will be covering in today's talk one, then we'll continue next, and then second technique. So we will be covering two techniques in our talk. One is state space averaging technique, then another is average switch modeling technique. Two approach we will be covering. And then there are multiple other approaches. Switching flow graph technique is there, energy factor approach is there, and other approaches are also there. But this first one is very popular, that we will cover in detail, and we'll try to get the various transfer functions well. So there are, as the name suggests, state space averaging technique. So what we do, we will obtain the state space model of the converter, right? Then we will do averaging, and then we will get the transfer functions. So it has three steps. The step one says that we will formulate the state space model of the converter in different modes. Then we will average, in second step, we will average out these state space model over one switching cycle to get the average state space equations. Then we will, in third step, we will linearize around a DC operating point, right? We will introduce the perturbation and we will get different AC model and DC model. Well, so the step one, formulation of state space equations, right? So as we have discussed that there are two modes, one is CCM, one is DCM. So in CCM, if there is one switch, then we have two modes. When switch is on, switch is off, switch is on, and switch is off. Two modes are there, right? So in these two modes, converter has certain a circuit. Then in another mode, converter has another circuit, right? Depending upon the switch position. So if there are more number of switches, then there is possibility that number of modes may be more than two. Number of modes may be more than two. Similarly, when we have discontinuous current conduction mode, DCM. So in DCM also, switch has three modes, at least three modes. One switch is on, another switch is off. Then when switch is off, within that, when inductor current is zero. So three modes. It means whether it's a DCM mode or CCM modes, a converter may have at least two modes or maximum maybe three mode, four mode, five mode, depending upon the switches, right? Now these converters are called variable structure systems. Variable structure systems, VSS. What is meaning of that variable structure systems? Variable structure systems means they change the structure with the time. When switch is on, some other structure; when switch is off, then other structure. So the structure keeps on varying depending upon the switching. It's keep on switching, right? That's why it's a variable structure system. So we will consider in our discussion only CCM mode, right? So let's say one converter is there which has two modes. For simplification, only one switch and two mode, and it is operating in CCM. Now when switch is on, then let's say that we will discuss. Let's say this is the DC to DC converter. So this is the switch, right? So when switch is on, this switch is on, it has mode 1, mode 1. When switch is off, then it has mode 2, right? So this switch is now off, it has mode 2, mode 1, mode 2. So when mode 1 is there, when switch is on, then it will have certain dynamics, right? And those dynamics we formulate in terms of state space model. In control system, we all study this state space model. X dot equal to what would we do read in control system? X dot equal to AX plus B U, Y equal to CX plus DU. That we read in control system, right? Where A is the system matrix, B is the input matrix, C is the uh, output matrix, like that. Y is the output variable, X is the state variable, right? Use the input variable or disturbance variable. Like that we do represent in control system, right? So in the same form, we do represent our converter also. Here I have written AX plus BU plus and by equal to CX plus EU. Instead of D, I have taken CE. The only reason is that B is used for duty cycle in converter, so we are using E. There is no other reason. That is the only reason, right? So when this subscript one denotes that it is for switch on. So we can use this subscript one or we can use on also. Either of the subscripts we can use here, A1 or A1, like that, right? So we write dx upon dt equal to A1 xt plus B1 ut, y equal to C1 xt plus E1 ut. This is in mode 1. Now what is the x in our case? X in our case is This is the state vector. So we take all inductor current and all voltage across the capacitors. So we choose state variables. So state variables are chosen as inductor current and capacitor voltages. So if there is only, so this is n cross 1 vector, right? N cross 1 vector and rows 1 vector. So if there is only one inductor, one capacitor, then value of n will be 2, and this will be just 2 by 1 vector, like IL and VC, right? If there is only one inductor, one capacitor, then one IL, one VC. If there is, let's say, two inductor, two capacitor, one capacitor, so this is third order. This is third order system. In this case, there will be two inductor current IL1, IL2 and VC1, and capacitor will be only VC, right? There can be combination one inductor, two capacitor. In that case, this will be IL, VC1, VC2, right? There may be fourth order converter also, two inductor, two capacitor, or maybe one inductor, three capacitor, maybe three inductor, one capacitor. So depending upon topologies, there are various topologies. We choose this X, but this X is chosen out of inductor current and inductor voltages. So number of inductors and number of capacitors will decide the order of N, right? Similarly, when switch is off, and the duration for that is 1 minus d into t, we write again the state space model. We obtain again the state space model for this converter, and in the same form we do write it: dx equal to a2 xt plus b2 ut, y equal to c2 xt plus e2 ut. So these two models are obtained, right, individually. Now, what we do next step, we do averaging of these state space models, right? Averaging of these state space models. So how the averaging is being done? So I just, yeah. So I write with some different, yeah. So we do multiply this with d into t, and we do multiply this in with 1 minus d into t, right? And then divide by the t. That's how we do. So if I multiply this a1, let's say first term only, dxt upon dt multiply with dt plus again dx upon dt multiply with 1 minus d equal to a1x plus b1u multiply by d plus a2x plus a b2u multiply with 1 minus dt, right? And then divide by t, because I need to take averaging. So just I divide by t, right? So I just write it dt and 1 minus dt divided by t. So t will cancel out. So what is left here? a1d plus a2 1 minus d into x plus b1d plus v2 1 minus d into u, right? So same thing I'm writing here, and here it will be dy dt xt into d plus xt 1 minus d, right? So 1 minus d plus d becomes 1, so it becomes only dxt only, right? Dxt. So this is dxt equal to, now this term I am denoting with a dash, this term I am denoting with b dash. So this becomes dx upon dt equal to a dash x plus v dash u, where a dash is nothing but a1d plus a2 1 minus d, b dash is nothing but b1d plus v2 1 minus d, right? Similarly, y, I can write for y. So yeah, this one. So y into d plus y into 1 minus d equal to here c1x plus e1 u C1x plus even u into d plus C2x plus E2u into 1 minus d. Right, so t I have already removed by taking average kind of thing. So this is why d plus 1 minus d is 1 equal to C1 d plus C2 1 minus d into x plus E1 d plus E2 1 minus d into u. Right, so I am writing this to be C dash x plus E dash u. So this is C dash x plus E dash u, where C dash is C1d plus C2 1 minus d. E dash is equal to E1d plus E2 1 minus d. So this model which I am getting here, this is called a non-linear averaged large signal model of DC to DC converter. What is the meaning of this? Let us understand. This is why non-linear, because here you can see this term a1 a dash xt. What is this term? A d plus a2 1 minus d into xt, right? So here this is a signal which is function of time, and this is also a signal which is also function of time. So it is a first order, it is a first order. When both multiply, it becomes second order. So a second order system, it is there and it is depending upon time also. So this system is non-linear. It is called averaged because we have just done averaging. So that's why it is averaged. And large signal model, why it is called large signal? Because it is having now small signal as well as DC. Like within this xt, its steady state value is there, its perturbation is there, original signal is there. So it is a complete model, large signal model. So far we have not done any approximation. So far we have not done approximation. We have just done averaging. So what does averaging means? Let's say there is some variable xt. This is t. So it is changing in this way. So what we do, we select one switching cycle, and within that switching cycle we do average this model. We do average. That's what averaging is called. Okay, so this is step 2. We have done averaging. We got this model. Now in step 3, what we do, we introduce perturbations and do linearization. So what is the meaning of perturbation? As I said earlier, that original signal is xt. Original signal is xt. Now we consider this signal as consist of two parts. One is x, which is the DC operating point or nominal values, right? And we near this nominal value we introduce some variations. So in every signal we do this. So xt we do it because xt is nothing but inductors current and capacitors voltage. Same thing we do in y also, which is the output voltage, right? DC value and its variation. Same we do in input signal u plus u cap d u cap. So somewhere you will see like written as a tilde, somewhere you will see written as a cap. So both are valid. Then duty cycle, so we consider its nominal value and variations. So these small x cap t, y cap t, u cap t, d cap t, all these are called variations or perturbations. These are called perturbations, right? Now these perturbations value is obviously very very less than this x. This perturbation value is very very less than their DC, respective DC values, right? Now one more thing, why we are doing this introducing perturbation, why we are doing, because we want to linearize the system around DC operating point or nominal operating point. What is that? So let us again take this is a system and 0, and this is f of x, and this is some x variable is there. Now This is how the system is working, right? But when x is varying, then the system is varying. But most of the time, my system is working at a nominal point. Let's say this x equal to x, right? Now what I want, if there is slight variation near this x, if there is any slight variation near this x, that is always possible. Then what I want, that near this operating point, I want to linearize this my curve or my characteristics or my dynamics. So if I linearize around this operating point, then my dynamics will be somewhat here, right? So my linearized model will be holding true only when there is small variation which is near to this DC operating point. But if variations is more, huh, beyond this, then this model or this linear model will not represent the original system. But if variation is less, then this linearized equation, this linear model will represent my original system. So that's what the meaning of linearization here is. So that we normally do in control system when there is a non-linear dynamics, because we have most of the tools which are easily available, less costly, linear tools, linear control tools. So we try that if we know the operating point, nominal points, then we do linearization of we do linearization around the DC operating point, and then design the control. So that's what we are doing. That is the purpose we have introduced these perturbations over here. Okay. Now, after introducing perturbations, how these equations behaves, that we will see. So our original equations are here. Now I am replacing this. So let me write here. So I'm just writing this dxt, for dxt upon d, I am just writing x dot t is equal to a dash xt plus b dash ut yt equal to c dash xt plus e dash ut. That's what our equation is there. And a dash is nothing but a1d plus a2 1 minus d, and like that. B dash is b1d plus b2 1 minus d, and c dash is c1d plus c2 1 minus d, and e dash is e1d plus e2 1 minus d, right? Now I am introducing this perturbation here. So x dot, I am saying x dot plus x tilde dot t equal to a dash is a1, then d plus d cap plus a2 1 minus d minus d cap. So this is a dash. X I am replacing with x plus x cap, plus b I am replacing with b1 d plus b2 1 minus d, right? Then u plus u cap. Okay. So if I simplify this, then this is a1d plus a2 1 minus d. Sorry, this, yeah, a1d plus a2 minus d plus a1 minus a2 d cap x plus x cap plus. If I simplify this, this is b1d plus b2 1 minus d plus d cap b1 minus b2 u plus u cap. Okay. So now I'm representing this quantity with A, this quantity with B. Remember that there is difference between this A dash and this A. This A dash was having, A dash was equal to A1D plus A2 1 minus D, and D is the small d here, which is function of time, But here in this capital A, this D are capital D, which is a nominal value. So there is difference between these two, right? So okay, so I again open this, and this becomes AX plus A x cap plus A1 minus A2 x d cap plus A1 minus A2 dx cap plus BU plus BU cap plus uh, B1 minus B2 U D plus V1 minus B2 D U. Okay, so this is the thing. Now this is we have not done any approximation so far here. Okay, so what I'm doing, I'm taking just AX to be together plus BU. So this is okay, this is okay. Now plus AX cap, this is okay, plus BU cap plus here D is common in both. So I'm taking D in common. A1 minus A2X plus B1 minus B2U D cap. So this term is also over. Now what is left with this term? A1 minus A2 D cap X cap plus B1 minus B2 D U cap, right? And this side is, it is X plus XT. Well, so now we want to linearize this, right? So if we want to linearize, then what we will do? We will neglect the first order term, neglect the all terms which is greater than first order. It means this term is constant, so I can write this as it is x plus bu plus this term is first order. I can write ax plus bu, right? Plus now a1 minus a2x plus b1 minus b2u. This is a constant term, and I am writing this new term as a bd, bd and d cap. So this is first order term, but this term is second order term. This term is second order term. It means it is multiplication of d into x, here d into u. So this is second order. Now if I want to linearize this system, then I have to neglect these things. So second order terms we need to neglect in order to linearize the transfer function, because our aim is to linearize it around the DC operating point. So that way we will neglect it. Now it is neglected. So this model is linear model, but this is for just x. So same thing I can do in by, right? And if same thing I do in by, then what is the y? Y equal to like this, and it will be cx. I'm directly writing now plus cx cap plus eu cap plus edd, where c is equal to so this is our final model, where a is equal to a1d plus a2 1 minus d, b is equal to b1d plus b2 1 minus d, c equal to c1d plus c2 1 minus d, and e is equal to e1d plus e2 1 minus d. There are two more terms, vd. So vd is yeah, this was the bd. Here this term we defined as bd, this term. So this is a1 minus a2 x plus b1 minus b2 u, and ed is nothing but this is c1 minus c2 x plus e1 minus e2 u, right? So these six terms are fixed terms. They are fixed terms, and they will depend upon system parameters. They will depend upon system parameters, right? So these terms are obtained. Now this model which we are having, this model is linearized model. Linearized model. Also this is state space averaged. State space averaged. But this is large signal. This is again large signal, because in this we have both the terms. uh, Steady state as well as small signal. One more thing we can write, x is the fix. That's why x dot we can write as 0, right? X dot we can write as 0. Well, so these equations, what we have just written, are simplified written over here also. Okay, so this is just written like that. So this x dot can be considered to be 0, right? Because it is fixed. Now after this, in next step, what we can do, because this is fixed, this is called steady state model, and this is Perturb term, this is Perturb term, this is Perturb term, and this is also Perturb term, right? So what we can do, we can separate out these steady state terms and these dynamic terms. We can separate out these steady state terms and dynamic terms. Any questions, please? Let me give 2 minutes break, and any questions, please? This is very important, those who are working on converters and their applications in microgrids and EVs, especially on controller side. If there is any question, please ask. Okay, so if there is no question, let us quickly finish on this topic. So we will segregate this steady state model and the dynamic model by taking uh, we equate the steady state value on both sides together and then perturbed value together. So the first model is called steady state model or DC model. Steady state model or DC model. So this here, this 0 is equal to x plus bu, y equal to cx plus u. That's what we write. 0 equal to x plus bu, y equal to cx plus u. If you simplify this, then this becomes minus ax equal to bu, and you can pre-multiply. Just you can write ax equal to minus bu. Now you can pre-multiply a inverse both the side. So this becomes like this. A inverse into A is the identity matrix. Multiply by X is X itself minus A inverse BU. So this is the X we get. Now we put this value in this Y. So Y equal to C X minus A inverse BU plus EU. So U will take common. It becomes minus C A inverse B plus E. Right? So this is the value of y. Now what is this x, capital X and capital Y? Capital X and capital Y. What was the small x we have chosen? We have chosen small x to be inductor current and capacitor voltage as a function of time, and Y we have chosen as output voltage. So what is then capital X? This is the DC value or average value. Y, what is the capital Y? V naught. So these two expressions gives us the DC values of DC values of these uh, uh, converter variables, output variable and the state space variables, which are basically inductor current and capacitor voltage. Right. Now the second, so from this we can find the steady state model. Second is the small signal model, dynamic model or AC model. Small signal model or dynamic model or AC model. So for that purpose, we just equate this x cap. So this is differentiation term equal to this entire term. So x cap t equal to ax cap plus bu cap plus bd d cap, yt equal to cx cap plus eu cap plus ed d cap, where bd is that we have already written. Now this model is state space model, right? It's in time domain. If we have any technique which can be used for such systems, for time domain systems, then we can directly use this particular system, this particular model, and directly use this for uh, controller design. But if we need transfer functions, we have some techniques which are useful for transfer functions, which are useful for linear controllers, then we go for its Laplace transform, right? So what we do, we take its Laplace transform. So Laplace transform of xscape is basically s into x of s, right? So the Laplace transform of this is basically s into x of s, not s into x of s minus x of 0, right? But because we are trying to obtain the transfer function, that's why we keep this initial conditions to be 0. So it is written only as x cap of s equal to a x of s plus b u of s plus bd d of s, y cx of s plus e u of s plus ed d of s, right? So these two equations are obtained. Now we will simplify these equations. So from here, if I simplify this equation, then what I'm getting, I take s, right, I minus, because s is the only variable, scalar variable. So I need to write a matrix in multiplication to this minus a, si minus a, and this x of s is this side, so x of s is equal to b u of s plus bd d of s, right? Now similarly, so from here x of s is equal to, because I can pre-multiply s I minus a inverse both sides, so this becomes unity. So here it is si minus a inverse b u of s plus si minus a inverse bd d of s, right? So basically this equation I have obtained. And if I put x of s here back, then what I get, y of s is equal to c si minus a inverse b u of s plus si minus a inverse bd d of s plus e u of s plus ed d of s, right? So this u is coming here, u is coming here. So if I take this to be common, then c si minus a inverse b plus e u of s plus c si minus a inverse bd plus ed d of s, right? So after simplification, I'm getting this expression, right? This expression, same expression here. Now what these expressions are giving me, right? They are giving me information that how dynamics of this x will change if there is any change in u and any change in d. How the dynamics of this y will change if there is any change in u, or is there any change in, so just write this here, c si minus a inverse b plus e into u of s plus c si minus a inverse bd plus ed d of s, right? So how this dynamics of y will change if there is any variation in u, and is there any variation in d, right? So I have already told you what is x and what is y, but what is d? D is the control variable. That is very important, that has to be there. And u is basically nothing but this is disturbance. So what is the possible disturbance? Possible disturbance is the change in input voltage, change in input voltage, and d, oh sorry, second is that change in load current, I naught or I z, change in load current, because change we have already defined them. There is two possibility of disturbances. One is line regulation, change in input voltage, another is change in load voltage. So that two possibilities there. So two kind of disturbance may exist. So what is the dynamics of converter if these disturbances are there? So these transfer functions relates that, right? So yes. So I have written here that U is this one. Let's say disturbance in input and disturbance in load current. Okay. So there is three inputs: V input, IZ, and D. So with these three disturbance, these three variables, out of which two are disturbance, one is control variable, there are three associated matrices. There are three associated matrices, and based upon these transfer functions, we can obtain many transfer functions, right? So let's say if it is I am having buck converter, which is having X as IL and VC only, right? So what is the transfer functions which I can obtain? So from here I can get one transfer function which gives me IL with respect to V in variation. Another is IL with respect to IZ variation. Third, IL with respect to duty cycle variation. Next, change in capacitor voltage with respect to V in variation. Change in capacitor voltage with respect to variation in load current. Change in capacitor voltage with respect to change in duty cycle, right? So 6 transfer functions. Similarly, if this variable is output voltage, then what I can get here, output voltage with respect to V input, and output voltage with respect to IZ, and output voltage with respect to duty cycle. So I can get 6 plus 3, 9 transfer functions with me. I can get 6 plus 3, 9 transfer functions to analyze the entire converter, right? Similarly, if it is the fourth order, converter, so let's say I have fourth order converter IL1, IL2, VC1, VC2. Then how many transfer functions I can get? IL1 upon V in, IL1 upon IZ, right? IL upon D. 3 transfer function. Similarly, 3 for this, 3 for this, 3 for this. So total 3 into 4, how many? 12. And then for output, V output upon V input, V output upon IZ, and V output upon D. 3 this. So 14 plus 3. It means 15 transfer function I can obtain, right? So all these 15 transfer functions are not useful for controller design. They are some transfer functions are just for analyzing the impact of different variations. But the transfer functions which are with respect to duty cycle, V naught upon D, IL upon G, these transfer functions are very important for controller design point of view, because these the control variable, and any change in input voltage, any change in the load current, that should be reflected by duty cycle itself, right? So change in duty cycle is important, right? Now what we are observing here, that this Si minus A inverse is coming everywhere. Si minus A inverse is coming everywhere, and this need to be computed, right? A is with us, then we need to compute Si minus A inverse. C is with us, and everything is with us. Just we need to compute these matrices, and using the these are matrix, right? Having constant things. So matrix solving is quite easy using the tools, MATLAB tools, etc. Right? That is the reason that this state space averaging technique is very popular for even higher order systems. Right? So this Si minus A inverse calculation has some issues. I will tell in next class, and this is called resolvent matrix. Resolvent matrix. and when the order of the converter is very high, or the converter involves uh, known identities, then the computation of resolvent matrix becomes a bit tedious, prone to errors, right? Cumbersome. So we will find out one algorithm called Laverel algorithm to simplify the calculation of Si minus A inverse resolvent matrix, right? So depending upon, like I said, second order converter, there is 9 transfer function possible. For fourth order, there is 15. Can any one of you tell me, please, how many transfer function will be there if order of converter is third order using this calculation? Please put in chat box if any one of you are answering, then it's good for me. Please tell me if there is order, third order is there, then how many? You can, your answer may be wrong also, just you try. How many transfer function will be possible? You put your answer in chat box. You can put your answer in chat box stating how many transfer function will be there if order is third. So it's a 12, right? So if it's a third order, then 3 into 3, 9. 9 plus 3. Total 12 transfer function will be possible, right? So we'll go ahead in this discussion further in the coming 3 days. So with this, I complete from my side. If you have any question, please let me ask. You can ask me question if you have any question related to today's talk. If you have any questions, please ask. Any questions, please? Number of transfer functions, how to decide? Okay, madam. Okay. I just explained this in the slide. Okay. Number of transfer function will depend upon the order of the transfer, order of the system, right? And order of the system depends upon number of energy storage element, capacitors and inductors. So as I said, let's say there are buck converter is there, and only it is having second order. So one variable is IL and one is VC, right? And we have two disturbances present here and one control signal. So if there is any change in this disturbance, then it will impact all transfer function. So if I want to see the impact on IL, so first disturbance, second disturbance, third is control. So total is 3. Now second state variable is VC. So 1, 2, 3, again 3. So if there, so it means we have 3 variables and 2 state variables. So total 6. If there is 3 state variables, 9. If 4 state variables, 12. If 5 state variables, fifth order, then 15, like that. So that calculation will be from here. Then from output side, we have only one variable, output voltage, and we have again 3 disturbances. So total transfer function is 3 here. If there was 2 output variables, then it could be 6. If there is 3 output variable, then it could be 9, right? But generally there is one output variable. So based upon that, 3 from here, and if it is 6, second order, then 6 from here, total 9, right? So if it is fourth order, then 4 into 3, 12 plus 3, that is 15. So if it is third order, then 3 into 3, 9 plus 3, that is 12. So this is how we are calculating this transfer functions, number of transfer functions. This is generalized way we are discussing, but not necessary that all transfer functions need to be calculated, right? If there is no disturbance present, v in iz is not present, then we will getting only two transfer functions from here and one from down. So total three transfer functions only. I hope I was able to answer your query partially. Thank you, ma'am. Okay, so with this we end today's talk, and yeah, thank you. So we will meet tomorrow again with new experts, new topics, and I will continue the discussion. We will be discussing how to obtain the transfer functions for various converters and how to design the controllers, then their applications. Like that, we will be talking. Jay Kumar ji. Any question from Jay Kumar? Please type. Any question? Please type. Okay, so with this note, we close today's session. Thank you very much. Thank you. So, Anupam, we can close today's session.
Okay, sir.
You can
Thank you,
create
sir, for your time.
just a minute tomorrow. Just a minute, Anupam. Tomorrow you need to you stop recording. Tomorrow, what time you need to create? Just I'm seeing the schedule. Tomorrow is 26th, na? है ना?